Now, when it comes to predicting the occurrence of earthquakes, definitely geology is still in its young science because it's very hard to actually predict the occurrence of any one specific earthquake. Now, I can pretty much for sure make this statement. There will be an earthquake in Asia very soon. Well, duh. It's in a convergent boundary. It's in the hazard zone. So you do have a general idea of areas in the world which are more likely to experience earthquakes because they're near tectonic plate boundaries. Now, we already talked about this in previous videos. For example, in the U.S., you have this area here which has the transform boundary in California and the convergent boundary where the North American plate hits the Pacific plate. And you also have the old fault line of New Madrid, which also causes some very, very strong earthquakes. So these hazard zones are areas which do tend to experience a lot of amounts of earthquakes. And especially in areas where you have very, very close to actual active boundaries where the plates are still moving next to each other. Now, in order to actually predict any one given specific earthquake, we got to do a little bit better than that. Now, one thing that scientists have tried to use in the past is the idea of a seismic gap. Now, a seismic gap is basically an area along a fault line that has not yet received a very strong earthquake in a long period of time. So, for example, look at the San Andreas Fault in California. The areas in blue here represent areas which have not experienced earthquakes recently, but that's because the faults are actually creeping and there's not actually large faults in that area. So the actual lines are actually sliding past each other, so that's not actually happened. Then you have the areas in red, which represents areas where movement is happening, but the fault is not creeping. That means it's locked, and therefore the rocks in that area are under tension, or in this case, under shear stress. And yet they have not yet released an earthquake very often. Notice, for example, that the areas south of Juan Batista actually experienced a lot of earthquakes in a recent amount of times, but between Santa Cruz and San Juan Batista, there hadn't been many earthquakes before 1989. You see that? Barely any earthquakes in that area. And so scientists thought that, wait, you know what? That's a locked fault area. We have not a lot of earthquakes. That means these rocks are just about ready to go. They're under a lot of tension. They're not that tough rocks, and an earthquake hasn't happened in a very long time. This fault line must be ready to go. And right after 1989, voila, massive earthquakes happen along the San Andreas Fault, and now you don't have that gap anymore. But you still have this gap here where not a lot of earthquakes have happened, and it's pretty sure that very soon another big earthquake will probably happen between Santa Cruz and San Francisco, and that actually subsequently happened a little bit after that. And so you see how scientists can use areas which usually experience earthquakes but haven't experienced it in a while as evidence of a future earthquake. That's called seismic gap. Another thing that actually sometimes helps is the ideas of a foreshock. Now, sometimes smaller earthquakes will happen before larger earthquakes happen, and usually this is an evidence of a lot of stress build up in that fault line. And remember, those foreshocks can be just enough to set off the destruction or a rupture of a larger rock, which then can cause a massive earthquake. So sometimes foreshocks, the problem is that foreshocks don't always precede the occurrence of large earthquakes. So that's not a very accurate way to determining it. Just like seismic gaps don't tell you exactly when it's actually going to give. It just tells you that it's about to give, but you don't have a really close prediction. Scientists said it's going to happen in the next 10 years. That's not really close enough. Do I take my earthquake here today? Is it going to have an earthquake? You can't really forecast that the way we forecast weather or climate or things like that. Now, another more accurate way to actually predict earthquake changes is look at rock changes. There are some areas in the world that have a lot of natural gas. And when you see this area that's full of natural gas, and all of a sudden you see a sudden release of the natural gas near the surface, which actually sometimes causes animals to die, and it causes changes in the atmospheric color. All these things could happen because a crack in the floor opened up because the rock deformed so much that it actually opened enough space for natural gas from deep underground to seep to the surface. That's usually an indication that this rock is under a massive amount of strain. It's actually changed so much that the actual gas is allowed to seep through the rock. And so that's definitely an indication of a massive change in the rock. Another thing you can look at is actually do something that's called earthquake lights. There's very little evidence for this, but you see them here in the bottom. These are atmospheric phenomena that seems to happen shortly before some massive earthquakes. It's been detected several times in the last 20 years, and we're finding that to be more and more the case before massive earthquakes. And scientists are still puzzled as to what would be causing this. Some people think it's because of electromagnetic disturbances that happen during the rock motions or the magma motion that's happening underneath that actually ends up setting off the earthquake. Other people think that it's a sudden release of energy that actually shakes the atmosphere, causing the atmosphere to change colors. We don't know what's actually happening, but we know for sure that sometimes right before an earthquake, the atmosphere makes this weird pattern of colors, which we call the earthquake lights. Also, we can actually look at GPS monitoring to actually see how much a rock is bulging. Remember, we talked about that right before the earthquake, the rock is usually bulged up. And so you can actually track the amount of change in the rock itself, or how much movement is happening around the rock using the GPS. And that's actually what we use nowadays to calculate moment of magnitude, because after the earthquake we can see how much the GPS trackers have moved in relationship to each other, so we can tell how much movement actually happened in the fall. But we can actually track that also through the bulging, because as the rocks bulge, the GPS will move. So for example, if you have an area that's being compressed, so that's how it used to be before, like that. And so the GPS unit was here, another one was there. Now that the compression took place, they're much closer to each other. And so you notice that the distance between them is becoming shorter. That's usually an indication of enough strain to actually make the rock kind of crack. And so that's usually what indicates that earthquake might actually happen. And then when you put that together with the composition of the rock, and you realize that the rock is this much tough or this much strong, and it can help you determine when this rock is finally going to give. Because remember, if you try to bend like a rubber band, it's going to last for a while before it actually crack. But if you actually try with the same thing with a piece of wood, it will crack way before the rubber band ever does. So the composition of the rock also matters. And when scientists are studying this, they look at the bulging together with what the rock is made of to try to make a prediction of how much tension this rock is under. And they actually do this for now. For example, you see this is a graph that's trying to show you how much movement the rock is under and how much stress they're in. And then considering how much tough this rock is, they can make a prediction about how close this rock is to giving. And yet, however, we're not that close to being able to predict earthquakes down to the date or even to the month. We can only make a kind of like a year prediction. It might happen this year. Looking at the seismic gap, looking at the hazard zone, looking at the amount of foreshocks, the amount of bulging, and everything that happens. All right? So the reliability, unfortunately, is not very strong, and it's all going to depend on our study of things like composition of the rocks, bulging of the rocks, earthquake lights, natural gas seepage, hazard zones, seismic gaps, and foreshocks, so that we can get better at determining which areas of the world would be better, or more likely to have earthquakes. We have that picture on what we call the hazard zones, but we want to get better at actually predicting exactly which day that's going to happen. But so far, we're far from actually having that kind of accuracy or precision in the prediction of earthquakes. So keep an eye out for those earthquake lights, because they're definitely the only thing we know that seems to be an indication that an earthquake is just about to happen. But by then, it might be too late to do anything about it. By the way, the take-home point here is that earthquakes will tend to happen along hazard zones, so you do have to prepare, you do have to know safety rules, and you have to know that it's going to happen. It's part of the Earth's natural process. It tells us that the Earth is active, it tells us that there's volcanism, it tells us that seismic plate boundaries are moving, it tells us that the crust is deforming, it tells us subduction is taking place, that rifting is taking place, it tells us that there might be a hot spot of volcanic activity. It can help us to study the bottom of the Earth and the shape of the Earth. It tells us that the core is still active, and it's something that we have to learn to live with, because the Earth is not changing anytime soon, and earthquakes are going to be a part of our lives. So all we got to do is become better at actually predicting as much as we can, and become better at building buildings that can withstand the earthquake. But we have to shy at the greatness and power of nature, and how much it can actually change our lives in just a few seconds, just like that rock. It's changing after so much stress in just a few seconds. Next, we're going to talk about volcanoes. For now, stay hard and don't do anything that will not make your mama proud. See you guys later.